Hi, I'm Sebastian from the Technical University of Munich and BMW, and I will present you our work, Joint Auto-Distribution Filtering and Data Discovery Active Learning, presented at CVPR 2025. Let's dive into it. We go step by step, starting with our motivation. Active learning can help to select data for the increasing amount of data required by neural networks. Real-world scenarios like autonomous driving or mobile robotics contain auto-distribution (OOD) data and novel categories to discover. However, current scenarios and active learning approaches do not consider OOD data and novel categories simultaneously. Moreover, existing methods usually rely on additional models and data access. To address this gap, we introduce Open Set Discovery Active Learning, or STAL, a novel scenario that jointly describes the impurity of the unlabeled data pool containing OOD data with the incomplete knowledge of relevant classes reflecting discoverable novel categories. To solve this more realistic scenario, we propose joint auto-distribution filtering and data discovery active learning, the first approach being able to separate OOD from novel classes without additional model and data usage. Let's jump to our novel OSTAL scenario. OSTAL builds upon the classic pool-based active learning scenario, but assumes limited knowledge about the unlabeled set. The pool contains additional discoverable novel classes as well as OOD data. In a cyclic process, data should be selected including the undiscovered novel classes while avoiding OOD data. The collected data will be annotated by an oracle, and samples are additionally marked as potentially interesting or OOD. All data collected can be used for training, which concludes the cycle. The complex and more realistic OSTAL scenario introduces the more challenging task of separating interesting novel classes close to the known data distribution from OOD data. To address this problem while eliminating the necessity of additional models and data access, we propose Joda. Our approach entangles the three phases of training, OOD filtering, and data selection in an efficient way that require the task model only. For training, we employ a combination of the cross-entropy loss for INDI data and the outlier exposure loss for OOD data. Afterwards, we employ OOD filtering based on energy scores enriched by our outlier exposure loss. As a final step, we select samples based on CSUM-E, a metric that uses the quotients of inner to outer class distances, and again the energy score. We extend the CSUM score by a class balancing factor. To validate Joda, we perform extensive experiments on 18 different setups in over 9 dataset combinations, including, for example, Cypher 100 or ImageNet variants in places 365. We split a dataset to form known and novel discovery classes and combine it with a different dataset for OOD data. We measure the accuracy, selection precision, and class discovery. Over the different dataset combinations, INDI to OOD, or also discoverable class variations, unbalanced datasets, or different models, Joda outperforms in by far the most settings and metrics. A selection of experiments is shown below, where Joda outperforms existing methods in terms of accuracy and class discovery. For selection precision, Joda is improving with the amount of data, but only ranks second. It should be noted that the high selection precision of LF-OSA comes with the cost of a low class discovery, so Joda provides the best trade-off. In addition, it should be mentioned that Joda is indeed the only method without additional models and data access. In conclusion, Joda outperforms existing approaches underlining robustness for different models, dataset compositions, and unbalancing factors. Contrasting to most prior works, Joda does not need additional models or data access. These minimal requirements and robustness in various scenarios make Joda lightweight and easy to apply. Thank you for listening. Please find all further details in our paper or on our project page.